Okay, so what is the Coriolis acceleration, or the Coriolis force? It's really an imaginary force that is the result of a moving reference frame, so it's not real, and a lot of people find it mysterious. So in describing the acceleration of a point in space with respect to a moving reference frame, meaning you are sitting on the frame and you're watching the point in space, one of the terms of that acceleration expression is called the Coriolis acceleration, and a lot of people find it mysterious, so we want to derive it, get the physical meaning, and find out what it really means. So here, to visualize that, we have two coordinate systems on potatoes. One is our inertial frame that's not moving at all. Here is our reference frame, and here's just some random point in space. And we want to know, again, the acceleration of this point as viewed from reference frame that's not only moving but also rotating about, any axis. It doesn't have to be x, y, or z. It could be some omega vector. So anyways, going to the actual derivation, so again, Coriolis force or acceleration, it's an illusion of a force due to a changing reference frame. It's one of many terms. So first, to get to acceleration, we want to start with position, because then we can just differentiate twice. So first, to describe the position mathematically, we have our inertial frame right here, and here's our reference frame, and here's our point P. Now, I won't go into all the details of the notation because it would take forever, but this should give the general idea. So first we just do a basic position vector addition. We say the position of P with respect to our inertial frame is the vector connecting our inertial frame to the reference frame, and then the reference frame to point P. So this is listed right here. Now we describe these more mathematically. Capital letters represent x, y, z of the inertial coordinate system, and uncapitalized letter with respect to the reference frame. So now we've described our position equation mathematically, so now we want to differentiate it. So differentiating this first term, x, y, z with respect to a frame that's not moving, according to the chain rule, we have to first get x dot, y dot, z dot, and then x times I dot, j dot, k dot, the unit vectors. But we know that the unit vectors are not moving, of course, so this term is 0. So here we just have the velocity of a particle, p. Simple enough, almost trivially easy. Next, we have the velocity, similarly, of our coordinate system, inertial coordinate system that's moving, and next we have velocity of our point P with respect to the the reference coordinate system, and lastly, in differentiating the velocity of point P with respect to our reference frame, we do have a rotation component, that is x times the unit vector I dot, and similarly for y and z. So we represent that by omega cross the vector connecting P to our reference frame. So for those who aren't familiar, why do we represent rotation with the cross product? So first, we'll try to explain that here. Intuitively, the cross product means when you have two vectors that are perpendicular, their cross product will be 1 or -1 depending on their direction. And two vectors that are parallel, the cross product's going to be 0. So why does that matter for rotation? So if I show you here, say for instance, well, rotation is described as your axis of rotation cross your vector describing your points of the origin. So here we could say our point is here, and we're rotating about this axis. We'll call it z right now. So as you can see, there is a significant effect, a maximum effect on this vector when we rotate. And in the instantaneous moment when you start rotating, I start going this way, I'll put it like this, you see that this point starts moving in the direction actually of this vector at that instantaneous moment, and that's where the effect is going to be maximum. So of course, say I had a point out here that was very close to the axis of rotation. Its effect is going to be very small compared to, say, an axis that was perpendicular. So that's the idea behind the cross product. And for those who aren't familiar. So that's how we represent rotation. So anyways, going back, we've got the velocity terms. Now we just need to differentiate again to go from velocity to acceleration. So, stop it.